My name is Bailey Chapin, and this is my Physics 2211 Lab 5 on the falling slinky. First, let's look at the introduction or the purpose and goals of this lab. The purpose of this lab is to observe and analyze the motion of a stretched slinky that is released from rest and falls to the ground. I generated two position versus time graphs, one with the tracker, which is the experimental model, and one with GlowScript, which is the computational model. I then analyzed the effects of the gravity and the drag on the motion of the slinky, and then used the computational model to compare the two. Get into the key concepts. A main physics concept of this experiment is based on Newton's second law, which states the net force of an object is the change in momentum over time. This law can be further rearranged into the velocity update formula. The position update formula can also be derived from Newton's second law. The next key concept is the gravitational force, which in this case is near the Earth's surface. Here, the gravitational force equals the product of the object's mass and the acceleration due to gravity, which is lowercase g. This is in the negative j direction. The value of g on Earth is 9.8 meters per second squared. The last key concept is the drag force. Air particles in the air create drag force on objects that is in the opposite direction of the object's motion. In this lab, the drag force is in the positive y direction and uses the product of a drag coefficient, lowercase b, and the square of the magnitude of the object's velocity. The drag force increases with time as the magnitude of the vector of the object increases due to the force of gravity. For the last part of the introduction, we'll look at the system and a preview of the key findings. The system in this experiment is the slinky, and the surroundings are everything else. Preview of the key findings: the experimental model and the computational model match completely before the top of the slinky reaches the bottom of the slinky. Once the two start falling together, the computational model slightly overestimates the position of the bottom of the slinky. Here is the tracker analysis along with the initial conditions. The mass of the slinky is 0.2 grams, and the initial position of the bottom of the slinky was found using tracker and is listed here on the slide. Tracker was calibrated using the man's height of 1.75 meters, and the frame rate was 200 frames per second. Here are the initial conditions of the computational model. The mass of the slinky is still 0.2 grams, and the initial position is the same as found using the tracker analysis. The initial velocity is 0 because the slinky is released from rest. The coefficient of drag was determined from trial and error. Here are the physics equations that were inputted for the computational model. It should be noted that this calculation loop starts at t greater than 1.050 seconds because this is the time at which the top of the slinky matches the bottom of the slinky. In this code, W is the weight force of the slinky and Fd is the drag force. Fnet is the sum of these two. This code also includes the velocity and position update formula. Here is a graph of the models of the experimental versus the computational comparison. Both of the models lined up perfectly until the top of the slinky reaches the bottom of the slinky, because the bottom of the slinky was static in this experiment until then. The computational model, as you can see, overestimates the position of the bottom of the slinky. This is most likely due to the computational model not including the existing kinetic energy from the top portion of the slinky falling previously. Some of the possible sources of error. The main source of error was with tracker and not being able to mark the perfect position of the bottom of the slinky. There were also some issues with the video frame rate because the video was in slow motion. It should also be noted that tracker was calibrated using Veritasium's estimated height of 1.75 meters. For the first discussion question, we're going to look at why does the bottom of the slinky remain stationary after release. The stretched slinky has a spring force that is equal to the weight force that is acting on the bottom of the slinky. Due to this, the forces on the bottom of the slinky are balanced until the top of the slinky reaches the bottom. Once they come together, the slinky is at equilibrium, so there is no longer a spring force holding the bottom of the slinky up. Therefore, the whole slinky falls. The second discussion question we're going to look at is what if weight was added to the bottom of the slinky? Adding mass to the bottom of the slinky would not have an impact in the position of the bottom of the slinky when released. The slinky would be more extended originally, but this would cause a greater spring force which offsets the greater weight. The bottom of the slinky would therefore still remain stationary. This is also dependent on the spring constant and length of the spring as well, as this would not work if the slinky became overstretched or wasn't stiff enough. Thank you.